Hey guys, um, hello, how are you guys doing? So, in this video, I want to talk about something called an empirical cumulative distribution function, as ECDF. ECDF is a very important way through which you can analyze your data. It's a very nice technique of understanding how the data is present for you. So I had explained in the last video, I had told about the bee swarm plots where you can basically understand how the data is easily spread. So like you can see the voting pattern of Pennsylvania is like this. You say 30, so 10 records, 5 records, and the 30% for Pennsylvania. For Ohio, it's like this, say 10, 5 records, under 32%. So that is how, right? But when you have lot of data, when you have huge, say 10,000 records or 20,000 records, then displaying it in a BSwarm becomes difficult. The BSwarm plot cannot interpret the data properly. As you can see, the interpretation is a real pain here. You can't understand. So here, say it could be 1,000 records. So how is gonna point show all those 1,000 dots to you? It is really difficult, right? So that's why you have all this kind of crazy square. You can't really make any sense out of it. So in this situation, a very popular tool is called empirical cumulative distribution function, wherein you basically are trying to kind of cumulatively, you're trying to show at any how much percentage of data exists for a particular value. So what it means, if you look at this, you can say that, okay, 20% of the counties, that is 0 to 0.2 is 20%. 20% have 36% of 36 or less vote for Obama. So if you look, this number is 36, right? And this is 20. So 20% of the counties had less, had, had voting share less than 36%. If you look at this point, what it means, around 60% of counties had around voting share less than 46%. So this is, you can easily interpret the count of data for different values of your data say. So it is so easy to understand how much count of data exists for different values of your data, right? So you can say that, okay, how much percentage of voted people voted um, or less than 60%, how many people voted for me? So if you go to less than 60%, how many people voted? It would be, say, 0.85% people voted less. Uh, 85% of the counties voted less than 60%. So this is how you interpret it. Say, for example, if the graph works like this, you can say that there were more counties which voted less than 50%. So this is even bad for Obama. This seems to be a slightly better figure for Obama. And if you keep on, say, if you see like this is a very good figure for Obama because you can say that kind of 85% of the counties voted less than 70. Wow, that looks better than 85% of counties voted less than 60%, right? So this is a this is a way through which you can create your cumulative analysis of data. It's called empirical data. We see the empirical data distribution function. Okay, so how you can create it is pretty simple. You have to first sort your data. Say if I want to first sort, I want to do the analysis of the demographic share of swing states. First thing I'm gonna sort that. I'm gonna first sort the data. So here is it, my data, and I'm first sorting it here, right? This is my first step. Then once it is sorted, I have to go to create an array of the number of pointers. Okay, so if in case I have say 100 records, so I need to create an array of 100 like this up to point say to one, the last point. Okay, so I need to create an array for this. So how can I create? I can use the NP range to create a range to the end. So I can use the NP range to create like this to the last, and then divide it by the length. So it will give you 0.01 like this. You will get up to one. Okay. So one thing to understand is that this divide by division of an integer by an integer in Python 3 creates a float. Okay, in Python 3 dividing integer by integer creates a float, but in Python 2 this will create an integer. So to make it work in Python 2, you need to use a float function here and then call this, then only it will work in Python 2, right? So need to know that. And then you're going to create a plot of this, say put the x value as your given value, and the y would be the range, that is 0 to length 0.0.101 up to 1. That would be your y-axis. And key things to notice, you give a marker as dot, so you want to just put a dot, and you don't want to join those dots. You don't not interested in joining them. Just put a dot. That looks pretty cool. Then as usual, give a x-axis, y-axis, and give a margin, a buffer of 2% on all the sides, which you can give a buffer, which is good for displaying the graph. So this is how you create it. And I can create, we can even, as you can see, we can have multiple values of empirical distribution put together as well. As you can see can see the empirical cumulative distribution function for Pennsylvania, Ohio, Florida shown together, which explains even more to you. And I'm gonna practice this with you now. So first, I'm gonna define my ECDF function using the same logic. Get the data and length of data. Based on data, I'm gonna set the length. Say length is 100 records. Get the length data 100. Then I'm gonna sort it first, as I said. So I have a sorted information which comes in the actual x-axis. And using that, I'm gonna give you the y-axis, which will be 0.001 to 100, or based on the number of count. We are gonna return both of them. And I'm going to create, I have this input, which is the versicolors, the colors, the cluster length for versicolor species. And I pass it to this function ECDF to get the value of the x and y values for this plot. So let us call it like this. So yeah, it's called now. And once here, I'm creating a plot with the x and y. Set the line style to none. And if you don't set the line style, all right, we'll remove it. I'll show you how it comes out first. So you can see how it comes, because without the line style, it tends to connect those and it looks ugly, right? So, and marker, you should give a marker as dot to create a dot for that point. And from this, you can have a good understanding of your ECDF. You can see that from this, you can kind of understand that 60% of the petals have, say, less than, say, the length less than 4.5 centimeters. I suppose this is in centimeter. I think it's in centimeters. So for 60% of the flowers have less than 4.5 centimeter. So it gives you a good understanding of the data, right? So even as we saw earlier, you can kind of even have multiple fields displayed together. So I have three data frame X values, one for the Sentosa species petal length, versicolor petal length, and virginica petal length. So it's so simple. All I do is I have the data frame, right? So I'm gonna first make sure I get only the data that I need for setosa. So if I do like this, so I'm create this data frame. And when I do this, I will get true for those which are setosa, those rows which are for true for setosa species and those which are not. So once I pass this true false information in here, so I can get the values for only setosa. And from there, all I need is the column of length for setosa. So when I do this, I give the mention the column name I want. So I got the values for that column name. Same concept, I created the values for these three species. Then we got the ECDFs for values for X and Y for Setosa, Color, and Virginica. And you can, but then all we do is we plot all of them using the plt.plot, give the marker line style none dot, and then all you need to do, we are kind of setting up the legend saying a list of things that you're displaying. So it's a Setosa, what's the color, Virginica, blue. So if you just mention the location, lower left, or if you mention lower left, if you say left, it will come here. You can give the location here. And those colors are also the order in which you're displaying those colors. Name you can mention here. It's a tuple. Okay, so we give the X and Y labels, and when you show, you can easily have a very good understanding of the way the data is spread for the three petals, three species. So you can see that almost the lowest value for Virginica starts from 5.5 centimeter, and for it is 5. And it looks like majority of the values are say, or you can see that it is more limited. If you look at this, the values limits are lesser for what is for Setosa. Setosa has, this is the limit for Setosa, kind of, right? And Virginica has got a broader range of values. So like this, you have some sort of some simple analysis you can do. It's a very simple analysis. So I hope if you found this information and maybe you liked it also, found this useful, and please do hit the like and subscribe button if you like it, and please do hit the subscribe as well. And thanks again for watching this video, and be coming back in another video. Bye.